Hello, good morning. Today we are going to discuss the second portion or second half of our first module, that is modeling of our BJT. Okay, so before moving on to the modeling of BJT is a type of analysis of BJT. Okay, so how can we say? For a BJT, we were interested in finding out the working of a BJT as an amplifier. Okay, so for a BJT to work as an amplifier, we know our main aim of our BJT is to work as an amplifier. So our BJT to be worked as an amplifier, we know that it should work in which region? It should work in an active region, isn't it? It should work in an active region. Okay, so in an active region, that things we know. The forward bias, the junction J1 should be forward biased and junction J2 should be reverse biased. So, in order to analyze that whether our transistor or BJT is a good amplifier, we have to analyze the response. Okay, so in order to identify whether our amplifier is a good one, a better one, or a poorer one, we have to do the analysis. Okay, so we have to analyze our transistor. Okay, so we have already studied of one analysis which was DC. Okay, so we have to analyze our transistor, that is total analysis of our transistor is required for our designing of our transistor, okay, BJT, or designing of our amplifier. Okay, so in order to analyze this, we know that according to our superposition theorem, what is it? We have to find out the total response of a amplifier here. According to the superposition theorem, what we have studied is for a linear bilateral circuit containing linear sources, then the total response of the total response in the circuit will be equal to the sum of the individual response of each source, keeping all other sources short circuited. അല്ലേ, നമ്മൾ സൂപ്പർപോസിഷൻ തിയറി എന്താ പറയുന്നത്? ഒന്നിലധികം സോഴ്സസ് നമ്മുടെ കയ്യിലുണ്ടെങ്കിൽ നമ്മുടെ സർക്യൂട്ടിലെ ടോട്ടൽ റെസ്പോൺസ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഓരോ സോഴ്സ് മാത്രം ആക്ട് ചെയ്യുന്നതിൻ്റെ റെസ്പോൺസിൻ്റെ സമ്മായിരിക്കും എന്നാണ് പറഞ്ഞിരിക്കുന്നത്. സിമിലർലി ഹിയർ ഇൻ അവർ കേസ് വി ഹാവ് എന്താ DC സിഗ്നൽ ഉണ്ടല്ലേ ഫോർ ബയസിങ്. ഓക്കെ, സോ വി ഹാവ് ടു ഫൈൻഡ് ഔട്ട് DC റെസ്പോൺസ് ആൻഡ് വി ഹാവ് ടു ആംപ്ലിഫൈ അവർ AC signal. This is for amplification of the signal, and what is the other AC signal is for the AC signal is for analysis and DC signal is for our for biasing. So this is for our biasing. So this biasing helps to keep our amplifier to work in the active region. Okay, now so in an amplifier, to analyze the performance, we have to take the total response. So the total response is the sum of the DC response as well as the AC response. Okay, so the total response is the sum of the DC response as well as the AC response. So this DC response, we have studied this in our biasing, isn't it? So this DC response is already discussed in our biasing circuits. the stability factor, everything we have studied. Now we have to move on to the AC response. That is, in order to find out the AC response, we are giving the AC signal and we are taking the analysis. Okay. So what is the analysis we are taking? We are giving the AC signal and we are analyzing it. Okay. So we are going to do a small signal analysis. Okay. So why should I say small signal analysis? AC signal analysis is also of two types. What are the two types of AC signal analysis? It can be a small signal analysis or a large signal analysis. This large signal we can call it as power signals or power amplification, or this is small signal amplification. So first, in this first module we are studying on small signal analysis. Why are we taking small signal analysis? In order to keep if the signal is slow or the AC signal is small, then it is easy for us to keep our transistor in active mode of operation. So first we are taking a small AC signal and we are making our transistor to work in active mode, and we are going to find out what is the small signal AC response of our BJT or of our amplifier with BJT as a switch. Okay, so according to this, the total response we have to find out. The total response is the total the DC response and the AC response. The AC response can be analyzed by using a small signal or a large signal. The large signal amplifiers we call it as power amplifiers, and the small signal amplifiers are the normal amplifiers. And then in order to study the AC signal, first we have to study the circuit of a power amplifier. Okay, sorry, the circuit of a small signal amplifier. So in the last class itself I have already told you, or in the lesson 3 we have compared the different configurations of the or different configurations of the transistor working, and we have found out that there are common base, common emitter and common collector, in which common emitter has got many advantages than the other two. So I have already told at the same time that we are studying with the common emitter amplifier only because it is the most commonly used amplifier. So again I am starting with the common emitter amplifier only. So let me draw with the common emitter amplifier circuit. So I am drawing a common emitter amplifier circuit. This is VCC, collector, base, emitter terminal. So RC, there is an emitter resistance RE, R1 and R2 at a potential divider biasing circuit. Then there is a ground. Okay. So now this is the basic DC biasing circuit. Now we have to give an input signal, isn't it? So we have to give an AC signal. So in order to give an AC signal, I am connecting a resistance, source resistance and an AC signal source. So again I have connected an AC signal source. This is my input AC signal. Then signal source. In order to couple, we have two capacitors, that is C1, and in order to take the output and block the DC we have C2. So we have two capacitors, and I am connecting one more capacitor here, that is C3, that is a bypass capacitor. So this is the circuit for a common emitter amplifier circuit. Okay, so this is the circuit of a common emitter amplifier circuit. Okay, so let me explain it once more. So what I said, this is a common emitter amplifier circuit in which this is plus VCC, this is the ground, R1 and R2 are the potential divider circuit, RC is the collector resistance, RE is the emitter resistance, and there are three capacitors, C1, C2, C3. Then RE, RS, this is the AC input, and we have RS as the source input. Okay, so this is a circuit. in which we have seen that this is our input side. This is our input signal or the AC small signal I am giving. AC small input signal I am giving, and we have C1, C2, C3 capacitors are there. We have C1, C2, C3. So what I can call this capacitors, all the capacitors C1, C2, C3 value all have high capacitance. You should note that all have high capacitance. So what is the purpose of this capacitance? This C1 will block the DC, or this C1 will couple the input to the amplifier. Okay, it will couple the input source to the amplifier. So we can call it as a coupling capacitor, input coupling capacitor. Okay, so C1 value is very high, so it is an input coupling capacitor. It prevents any DC signal to enter into the biasing circuit. What is the capacitor? C2. C2 couples the circuit, amplifier circuit to the output circuit. So what will do? This C2 prevents the DC or blocks the DC. So this is also a coupling capacitor. The main function is that it blocks DC signal from the amplifier to the output source. So these two are coupling capacitors. Now we have one more capacitor, that is C3 capacitor. What is the purpose of this C3? This C3, this C value is very high. Why have we selected this C values as high capacitance? That is, the reactance Xc is equal to 1 by 2 pi Fc. As this C value is very high, then what will be there? The Xc value will be very low. That is, it acts as a short circuit at AC time. Okay, it acts as a short circuit of AC at the time of AC operation. Okay, so what will happen here is, this will act as a short circuit, or it bypasses the emitter resistance. Hence we can call it as a very important. Hence we can call this as a bypass capacitor. Okay, bypass capacitor, or in other words we can call it as an emitter bypass capacitor. Okay, we can call it as a bypass capacitor, or in short we can call it as an emitter bypass capacitor. Okay, so I hope you understood why we are adding high capacitance value, and also why we are having three capacitors. So these C1 and C2 are coupling capacitors, and this C3 is a bypass capacitor. Bypass capacitor bypasses the emitter resistance so that the losses over this Re can be overcome in the circuit, which we will discuss in our later time also. So this is a very important question. What is the significance of or what is the role of a coupling capacitance, and what is the role of a bypass capacitance in an amplifier circuit? Okay, so I hope you understood how to explain a common emitter amplifier circuit. This is the input. Every source will have a resistance, so I am connecting a series source resistance here. Then input coupling capacitor C1 is there. Then R1 and R2 are the potential divider biasing circuit. Why are we using this potential divider biasing circuit? Always is because of its flexibility in the design. This R1 and R2 will provide a low input or RB value to the circuit. It is easy to design, very flexible. Then RC collector resistance, and we have the emitter resistance RE in order to reduce the losses of the current flowing. If the current IE flows through RE, then the loss will be IE RE, or in order to reduce this losses, I square R losses, we are providing a bypass capacitor, that is C3, or we can call it as an emitter, bypass, capacitor. This is all about a common emitter amplifier circuit. Now, in order to do the AC analysis, what we have to do is we need to do our AC analysis in mainly we have to do in 2 steps. Okay. So I'm moving on to our AC analysis, especially small signal AC analysis. Okay, small signal AC analysis. In this can be performed by following 2 steps. What are the 2 steps which we require to follow? That is, in the first step, what we will do is, for analyzing, we know that we should convert all the elements into a simple equivalent circuit. What is an equivalent circuit? An equivalent circuit is a simplified circuit which consists of the basic components like voltage sources, resistance, inductance, current source. All those basic elements are arranged to best represent the behavior or the characteristics of a particular circuit. Okay, so while we are doing the same procedure here, we are going to represent this complex circuit in terms of a simple circuit. Okay, so what we are going to do is we are going to analyze our AC response of this particular amplifier circuit in mainly 2 steps. In the first step, what we will do is we will find out the equivalent circuit. Okay, we will solve for the equivalent circuit of this amplifier. So what we will do is we will rearrange the circuit and we will find out the equivalent circuit. So after the equivalent circuit, what will be the result? In the result, we have some equivalent elements, equivalent circuit elements like some RL or RLC or some voltage or current sources along with our BJT. Okay, we haven't changed our BJT. Okay, we haven't changed our BJT. So this BJT will be there as such, but this other elements will be simplified. We will check whether any elements were there in parallel or series so that we can simplify our circuit. Okay, so in the first step, we will find out the equivalent circuit. Now we have to transform this BJT. So this BJT will be replaced by its equivalent model. Okay, so this BJT will be replaced by its equivalent model. Okay, so what is an equivalent model? I have already told you, similar to the equivalent circuit, we say that equivalent model should also be found out. What is an equivalent model? For a definition, we can say equivalent model is the combination of the circuit elements properly chosen to best represent the actual behavior of the device under specific operating conditions. Okay, so I will give the equivalent model definition at that time. Okay, so first what I am going to do is I am going to find out the equivalent circuit. Okay, so first what we are going to find out? We are going to find out the equivalent circuit. Okay, so in order to find out the equivalent circuit, what I have to do is I have to follow 3 steps. Okay, in order to find out the equivalent circuit, what we will follow? We will follow 3 steps. So let us check what are the 3 steps required for the equivalent circuit. So this is very important for modeling. So I am writing on. We are going to find out the step 1, that is equivalent circuit. Okay, step 1, equivalent circuit. So how can I find out the equivalent circuit? First, this should be done in 3 steps. Okay, 1, 2, 3. So this should be done in 3 steps. So what I will do is, first I will remove all the DC sources, isn't it? We are finding out the AC response. So we have to short circuit all the DC sources because DC sources should be absent. So what I will do, I will short all the DC sources, or grounded, it will be grounded. Okay, so I will short circuit all the DC sources. So what we will do, we will give all the VCC to 0, short circuit, so it will be grounded. So in that we will VCC to ground, we will connect VCC to our ground. In the second step, this was my step A, first step. In the second step, what we will do, we know that we are going AC analysis, isn't it? We have already studied, we are selecting the capacitors of high capacitance. So as a result, what will happen? Under AC circuit, this capacitance is low, or I will short circuit all the capacitances also. I will short circuit all the capacitance also in the second step. As our capacitance are having high capacitance, the capacitive reactance will be very low, or the impedance or the reactance offered is very low, so the capacitors can be short circuited. So in the second step, I will short circuit all the capacitors, and the third step, it is very easy. I will make corresponding corresponding corrections, and we will redraw the circuit. Okay, so in this last step, what we will do, I will make these 2 modifications and I will redraw the circuit. This circuit which I am redrawn is the equivalent circuit. So what will be there in the equivalent circuit? In the equivalent circuit, there will be a BJT plus some basic circuit elements. Okay, some basic elements only. Okay, so this is an equivalent circuit, and this completely represents the behavior of this particular amplifier circuit. So shall we draw, or shall we construct our equivalent circuit? So I am going to construct our equivalent circuit. So this is our equivalent circuit. Okay, so what will I do with this equivalent circuit? I will tell you, wait. So in order to find out the equivalent circuit, what we have to do is, first we have to short circuit all the DC sources. So what should I do? I have to make it as a ground, isn't it? I have to make it as a ground. Now in the second step, what I have to make, I have to short circuit this C1 and C2. So what will be there? This is my ground, and this is short circuited. This is short circuited. Then this is also short circuited. What does this mean? This is short circuited means what is it? Most of the current, because this is short circuited, all the IE current will flow through this circuit only. All the IE current will flow through this circuit only. So what will happen? The RE resistance is bypassed, or there is no role for RA. So we don't have to draw this. Okay, so I am redrawing it. That is, so I am redrawing it as, we have resistances R1, VCC is grounded, then I am having this base, emitter, collector, and I have a collector resistance RC. RC is also grounded, isn't it? Now we have RE, but this RE is already shorted. So I am directly connecting it to the ground, and we have our resistance R2, that is also grounded. Then we are having our AC input and a source. Okay, so AC input and RS in series. R1 is grounded, R2 is there, we have base terminal. So what is the direction of base current? This is IB. Why am I using the small letter? Because we are finding out AC response. AC current only is there. Then this is our IC. Then this is IE. Through this our current IE will flow through. This is a simplified version of this particular circuit. Okay, so then if I am looking into it, then I can redraw our circuit as this is my AC source, this is my resistance RS, and when I look into this portion, here R1 is connected to ground as well as R2 is connected to ground, isn't it? So again, what can I do? I can redraw my circuit as this R1 and R2 parallel. Okay, so then how can I draw it? So I can replace it with a resistance R1 parallel R2. Okay, or I can call this as my resistance to the base. So I can call it as with a name RB. Okay, then it goes to my base terminal. Then the emitter is directly grounded and we are having the collector. So this is collector, emitter, base. Collector is having a resistance. That resistance is RC and it is also connected to ground. So this is the equivalent circuit. This is the equivalent circuit of a what? Equivalent circuit of our transistor. Okay, equivalent circuit of our amplifier. So it has all others are equivalent circuits or linear elements except this BJT. Okay, now we have to replace this BJT also with equivalent circuit elements. Okay, so in the first step we have drawn the equivalent circuit elements. Okay, we have drawn the equivalent circuit except that of the BJT. So first step is completed. So equivalent circuit step is completed. Okay. So in order to analyze our AC signal, first step is we have to find out the equivalent circuit. So I have drawn the equivalent circuit. I have got a resistance RS and a voltage source V input or Vs. Then I am having a resistance. This resistance I can call it as RB, or which will be R1 parallel R2 on simplification. This is my base terminal collector. This is my emitter. Emitter is also directly grounded. Then I am having my collector resistance over which I am connecting the output. So the output will be connected across this RC. Okay, so there is an RC and this is the output, and this portion I can call it as the input portion, collector, emitter, and this is grounded. Okay, so this is the equivalent circuit of our amplifier. Now what we have to discuss is we have to study the second step. What is the second step? Second step is equivalent model. Okay, so second step is equivalent model. So what is an equivalent model? Equivalent model. Okay, so an equivalent model can be defined as the combination of circuit elements. Okay, so it can be defined as a combination of simplified circuit elements. Combination of circuit elements properly chosen to best represent the actual performance, to best represent the actual performance, to best represent the actual performance. Okay, the actual performance of the devices under specific operating condition under specific operating point or under specific operating point. So what is an equivalent model? Equivalent model is a combination of circuit elements which are chosen to best represent the actual performance under specific Q point. Okay, so this equivalent model should represent the actual behavior of the BJT. So in here you should note that the BJT should what is the actual behavior of the BJT, or how should we represent the BJT? Here the BJT is working as an amplifier. For the BJT to be worked as an amplifier, it should be in the linear mode. So we should represent the linear model of the BJT. Okay, so corresponding to the equivalent models of the BJT, there are 3 equivalent models of the BJT is possible. Okay, there are 3 equivalent models of the BJT is possible. So what are the first one? We call it as hybrid model, which we will study in our first module itself. So first one is a hybrid model. The second one is R-E, or we can call it as dynamic resistance model. Dynamic resistance model. And the third one is a hybrid pi model. Okay, so we have 3 models. This we will study in our second module. So hybrid model is there, then a dynamic resistance model is there, hybrid pi model is there. This hybrid model, this will be in general terms. Okay, the transistor will be represented in general terms, like in our circuits and networks theorem. No, we will say for a linear bilateral active network with so and so, like that. No, so generally it will say like that. So this is a hybrid, means it represents the BJT in a general 2-port network, as a general 2-port network. Here the BJTs will be represented by using a resistance. Okay, as it is a linear element, it will be replaced with a dynamic resistance. Okay, and here it is a combination of hybrid model, or it is a modification of the hybrid model, which we will study in the second module. So these are the 3 equivalent circuit models of a BJT. So now I just want to tell you how can we represent a BJT. So first what I am doing is, for representing a BJT, just I am taking a common base NPN transistor. Okay, I am taking a common base NPN configuration. Then what will be the symbol? So common base, isn't it? So the base will be common. This is base, this is emitter, NPN, collector. Okay, so N emitter. So here we will collect the input, and here we will collect the output. Here we will give the input. So this is the symbol of a what circuit? This is the symbol of a NPN transistor. Okay, so what will happen here? The input is forward biased, isn't it? The inputs are, so this P is connected to the positive, and this is connected to the negative. Like this, we are forward biasing in. So in the forward biased circuit, how will this act? This will be a forward biased PN junction diode, isn't it? This will be a forward biased PN junction diode. So how can I draw this as a PN junction diode? I can draw this as this particular thing as, this is N and this is P, isn't it? So cathode and anode. So I can draw like this. Okay, so this is the similar to base and emitter here, and I am giving my input forward biased input here. Okay, so like this I am giving. Okay, then how can I replace my circuit? That is, What is it? This is a reverse biased junction. So in the reverse biased junction, what is the collector output? Here it is IE. IE direction is like this. IE is like this. So IB should be like this and IC should be like this. Okay. So what is IB and IC? Okay. So this is common base configuration. Okay. So what was the amplification? Amplification factor. You remember in common base configuration, alpha was the amplification factor, that is output current IC by IE. So I can write it as that is IC is equal to alpha times IE, isn't it? So IC is equal to alpha times IE. So this junction I can replace it with a current source, isn't it? That to a dependent current source. So what is this? This is my current direction. And what is this current direction? That is current is IC. The current is IC. That will be equal to alpha times IE. I can write like this. IC, or it is alpha times IE. Okay, in the current direction. And then what is the current IB then? The current IB will be flowing in this direction. So IB, what is IB? IB will be equal to, what is it? IC. What is the general equation? IE is equal to IC plus IB, isn't it? So what is IB? That is IE minus IC. So that is IE into 1 minus alpha, I can write, isn't it? So IB is equal to IE into 1 minus alpha. Why I am writing in terms of IE? Because IE is my input current. What is my input current? That is IE. IE is my input current. That's why I am writing in terms of IE. Okay. So IB is equal to IE into 1 minus alpha and IC is equal to alpha IE. So this will represent a behavior of this transistor, isn't it? This will represent the behavior of a transistor in the common base configuration, isn't it? Now again, if we want to modify, again we can modify, because our equivalent circuit should contain only what? It should contain only equivalent circuit elements. This diode is not an equivalent circuit element. It is not a simplified element. So this diode can be replaced with a resistance. How is? This is a forward biased diode, isn't it? How can we represent a forward biased diode? We can represent a forward biased diode by using its forward biased diode by using VI characteristics, isn't it? So what is this? What is this? This is V. This is I characteristics. And with the slope of this, okay, the slope gives RE, dynamic resistance RE. So with the slope, we can represent this diode. So how can I redraw this? Then I have a resistance. Then I have a current source like this. So IC is equal to alpha IE. And what is this? There is a resistance R dash E, or dynamic resistance. So this is the dynamic resistance model of a common base amplifier. This is the dynamic resistance model of a common base amplifier. Okay. So what is the current? Here it is IE, and here it is IB is equal to 1 minus alpha into IE, all written in terms of emitter terminal or emitter resistance. So we call it as emitter configuration. So can you draw it with our common emitter amplifier? This we have drawn with common base configuration, isn't it? So now we have to draw it with common emitter configuration. So how can I draw it with a common emitter configuration? That we will see once again. How can I draw it? Okay, so what is my common emitter amplifier or common emitter configuration? In a common emitter configuration, NPN transistor itself. So this is the emitter, this is the collector, this is the base, and this is the common one. Here I am giving the output. here I am giving the input and here I am giving the output. Okay, so emitter is common to the base and collector. Okay, this is our configuration. So how can I redraw it? Here this should be forward biased diode, isn't it? So what will be the condition of our diode? It is positive, negative. So my diode should be like this. So this is the diode and this is the emitter terminal. This is the diode. Then RE, I am writing it. Okay, this is the diode. Now what is it? Here, this what is the direction of collector current? IC. Here it is IB. Okay, so what is the relation alpha? Here the amplification factor is not alpha, amplification factor is beta, that is output current by input current. So I can write IC is equal to beta times IB, isn't it? So here I am having another source to represent this. This is beta times IB. So that is equal to IC. Beta times IB is equal to IC. Okay. So now what is IB? IB is the current flowing like this. So this is IB. Okay. So I can draw like this, isn't it? IB, beta times IB. And this is my collector terminal C. Now, how can I redraw it? So I can redraw. I can again simplify this with the help of a resistance, isn't it? So if I replace it with a resistance again, then it is collector. Then I am having a current source. Then there is my B terminal. Then I can replace it with a resistance RE. Because emitter resistance RE. This is a circuit. Okay, so if I am calculating the current IE, then I can say IE is equal to IB plus IC. Okay, so IE in general terms I can write it as IB plus IC, or I can say IB into 1 plus IC is beta IB, isn't it? So beta IB into 1 plus beta. Okay, so if I have to rewrite this, then IE that will be beta plus 1 into IB. Okay, now what my requirement is, I have to, in order to apply circuit theorems correctly, I have to separate the AC source as well as the DC source like this. Here the AC circuit is separated and the input circuit is separated as well as the output circuit is separated. Like this, I have to separate my input and output circuit. Then how can I redraw it? Then I can redraw my input current. This is input current. So I can redraw my input current, that is IB. My IB is coming and IB is coming through a resistance, that is RE. RE, if I am writing in terms of IB, you should listen. This is IE, current through IE, but I am representing in terms of IB. So then if I am representing in terms of IB, then it will be beta plus 1 into IE. Okay, so I can write this voltage across RE. Voltage across RE is equal to IB into RE, or I can say it as, IE into RE, or I can say it as beta plus 1 into IB into RE. So I am taking IB, then beta plus 1 into R dash E. Now I am connecting like this. Then I am also having an output source with current, that is IC is equal to beta IB. Okay, so I can replace like this. Okay, I can redraw my circuit. IE is equal to IB plus IC. Like this, I can separate my input and output sources. Okay, so finally, what we have to do is we have to replace our BJT. We have to replace this BJT in our original circuit with this circuit. Okay, so how can we do it? So this was our actual circuit, isn't it? This was our actual circuit. So I am going to redraw this actual circuit. Okay. So if I am redrawing it, then we are having a source resistance RS and a voltage source V in, and we are connecting like this, and we had a resistance that is RB, which was equal to R1 parallel R2, isn't it? This was there. Now we have to replace this BJT. How can I replace my BJT? Do you remember how can I replace this BJT? Here this current is IB, isn't it? This current is IB. So if I am redrawing it, then I am having a resistance. Do you remember that? I am having a resistance. The resistance R dash E into beta plus 1. Okay, R dash E into beta plus 1. And again I had a current source which was facing downwards, that is IC is equal to beta times IB. Okay, so I have separated the input circuit and the output circuit. So IC is equal to beta times IB. The current direction is facing downwards. So here I have separated the input circuit as well as the output circuit. So what I have done is I have replaced this BJT circuit with our equivalent model. Now what I have to do is I have to redraw the rest, that is RC. Okay, and so I am connecting our resistance RC. Okay, and we are collecting our output from this terminal. Okay, so I am connecting this output. So sometimes there is an output resistance RL. This is RC. So sometimes there is an output resistance RL or RS. Okay, so this is the equivalent circuit representation or equivalent circuit dynamic representation of a common emitter amplifier. With this simplified circuit, we can express or we can find out or analyze the response of our circuit. Okay, so what is this? This is the input terminal. So this is the input side, and what is this? This is the output side. Okay, so I can say this is a two-port network, and this is our common emitter amplifier circuit, simplified common emitter amplifier circuit. Okay, so with this two-port circuit, why do we need, or why are we solving like this? Because we have to find out the performance of this amplifier. What are the parameters to analyze the performance? Like that, if I am looking from here, I can find out what are the performance parameters. I can find out the voltage gain, that is AV is equal to output voltage by input voltage. I can find out the voltage gain, or I can find out the current gain, that is output current divided by input current, or I can find out the output resistance of the circuit. Okay, how can I find out the output resistance of the circuit? If I look from this portion, what is the Z0? This thing I can find out, or I can find out the input resistance, that is the resistance at this circuit. What is the input resistance of the circuit, or what is the output resistance of the circuit? Like this parameters we can solve by using the equivalent circuit model. Okay, so this is RE model, which is not at all important, which is not asked for our university question or in the syllabus. But why did I teach you this is just to make you understand that why we are solving for this hybrid model, or why we are solving for the equivalent model. Okay, so for a transistor, in order to analyze it, we have to find out the current or voltage in a circuit. Okay, so in order to find out the voltage or current in a circuit, we should apply network and circuit theorems in it. But for a practical element, it is very difficult to apply the circuit and network theorems in it. So what we are doing is, we are replacing the practical element in its equivalent model. What is equivalent model? Equivalent model consists of a combination of equivalent circuit elements or basic circuit elements which will best represent the actual performance of a practical circuit. So our equivalent model has a basic circuit elements which will represent the best character of the circuit. So, in order to apply the network theorems, we are changing our BJT or practical circuit into equivalent circuit. Then, after making it into the equivalent circuit or equivalent model, it is very easy to find out our circuit parameters. Okay, that's all for today. Thank you.